This picture shows the refueling machine of a CANDU reactor. One of its more interesting characteristics is the fact that the reactor can be online refueled. So while the reactor is still operating, they can turn off individual pressure tubes and then pull fuel out of those pressure tubes and put new fuel in. The coolant here only serves the purpose of keeping the fuel from clad from melting. The moderator itself, which is in this separate vehicle called the calandria, is a heavy water moderator. Since it has a heavy water moderator, it can use a natural uranium fuel. Heavy water absorbs a lot less neutrons than light water, and so therefore the fuel that's in the reactor does not need to be enriched. Another type of reactor, which you will not see very many of, but used to exist in a large number in the world, is graphite moderated reactors. In this case, the reactor uses a solid graphite moderator. That moderator then moderates the neutrons. Since graphite also absorbs very few neutrons compared to light water, this system also can use a natural uranium fuel in either oxide or metallic form. What's shown here is the Magnox reactor from Great Britain. The Magnox reactor uses a metallic uranium fuel, usually in a uranium alloy. And then it uses a gas coolant. In some of these cases, it can use a gas coolant in a Brayton cycle, or in some cases, it might use a light water coolant in a Rankine cycle, or even a gas coolant in a Rankine cycle. There are a number of different types of graphite moderated reactors. The picture that's shown here is actually from a design reactor called the HTGR. This is actually from one of the ones that was built here in the United States, I believe, is where that picture came from. This particular reactor, again, is a gas-cooled, graphite-moderated, natural uranium-fueled reactor. There's also the RBMK style reactor, which is the style that the Russians designed. The most famous one of those was the Chernobyl plant, which was an RBMK style reactors. There are not many, if any, RBMKs still operating in the world today, which is probably a good thing. And then, of course, there's also the HTGR type reactor, which is what's shown here in this picture. The last kind of reactor that we're going to talk about is the fast reactors. Fast reactor systems are actually a very complicated, very advanced technology. Very few states have developed this type of reactor system. They typically have 3 loops to it. So there's a primary loop, which is the one shown here, which flows through the reactor. That goes through a heat exchanger that goes to an intermediate loop, which then goes through a heat exchanger that goes to a third loop. The third loop, of course, is the one that actually then produces electricity. The intermediate stage is added into here because of the fact that the coolant that's used in this reactor becomes very, very radioactive. And it becomes so radioactive, in fact, that it can disassociate hydrogen out of water. And so this intermediate loop is there to provide a buffer between this radioactive coolant and the water loop, where this coolant that's in between here would be a non-radioactive metallic coolant. The most common version of this uses liquid metal as its coolant. The liquid metal can become very intensely radioactive. The liquid metal also typically is sodium-cooled liquid metal, or sodium liquid metal. And the sodium itself is fairly dangerous in that it catches fire in air and water and can cause some other difficulties. One nice thing about these reactors, they're extremely small. Typical size of a fast reactor is about the size of a trash can. So they're very compact. They will often use highly enriched uranium or plutonium as a driver fuel that is then surrounded by a depleted uranium or natural uranium blanket, and that blanket then is used to breed plutonium. And these particular cores are designed in such a way that they actually can produce more fuel than they consume. And so the typical analogy of this is it's similar to your car, in that with this type of reactor, as you operate the reactor, you actually make more fuel than you burn up, which is the same thing as you filling up your gas tank halfway, operating your car for a while, and when you stop, having the entire tank full. The coolant that's in here is usually, like I said, liquid metal or sodium, but there are types of reactors that have been designed of this type that use gas coolant instead of a liquid metal coolant. The liquid metal has some very excellent heat transfer properties, which is one of the really good reasons to use it. The gas coolant doesn't have nearly as good of heat transfer properties, but it does have some other advantages as well. Control characteristics for this reactor are very complicated. The design of the reactor is very complicated. The fuel manufacturing is difficult. And so this particular technology is very advanced, and only a few states have really ever mastered it. If we then look at what the production of material in an operating reactor is, this particular chart just shows the plutonium buildup in a pressurized water reactor, where you have the mass of plutonium, or concentration of plutonium, as a function of burnup. Burnup is the amount of energy liberated from the fuel per unit mass of the fuel. So if a reactor or if a fuel was operating at constant power, this x-axis would just translate to time. And so if I was running the reactor for a certain period of time, I would get a certain amount of plutonium. In this particular case, you can see the plutonium-239 builds up linearly at first, and then as I continue to operate the reactor, at some point in time, the plutonium-239 starts absorbing neutrons, and then it'll reach equilibrium inside the system, where the production of plutonium is equal to the destruction of plutonium due to fission, or due to absorption. This curve, actually, if one could keep taking this thing out, would actually start to come down. At some point, you would actually stop producing plutonium-239 and actually start absorbing it, and it'll start to decrease. But you have to get to really high burnups in order to do that. As I continue to burn the fuel, while I stop producing as much plutonium-239, I start producing more of the higher mass plutonium isotopes, like plutonium-241, plutonium-240, plutonium-241, plutonium-242, etc. If I just look at the total plutonium content of the fuel as a function of time, I get this curve, which shows that again, early on, the production of that is very linear, so up until about 10,000 megawatt days per metric ton. But as I continue to burn the reactor, at some point I am producing more energy, but not producing as much plutonium per unit time that I'm operating the core. What that tells me is that a particular operator of a reactor, if one wanted to operate a reactor for the purpose of producing plutonium, you would operate the fuel down in this lower area, where you'd be producing as much plutonium per unit time of operation as you possibly can. If somebody's operating a reactor for the purpose of power, they typically operate the fuel out in this area. And so typically what we expect to see is that if a fuel was operated for power, I would expect to see burnups in the order of 30, 40, 50 gigawatt days per ton. If it's operated in terms of plutonium production, I would expect to see lower burnups, 10,000 megawatt days per metric ton or lower. If I look at different types of reactors, you see similar curves. The amount of plutonium produced is different for different reactor types. So this is a very similar curve, just shows concentration of plutonium as a function of time or a function of burnup for PWR, BWR, CANDU, Magnox, etc., different types of reactors. And you see curves that are similar but not necessarily the exact same. But the same rule essentially still applies. In the case of the Magnox and CANDU reactors, those type of reactor systems, you typically can't operate the fuel beyond about 10,000 to 20,000 megawatt days per metric ton because there simply isn't enough U-235 in the fuel to keep it critical in the reactor. PWR and BW reactors, on the other hand, can operate to typically much higher burnups. So that goes through the basic types of nuclear reactors and some of the plutonium production that you might see for those systems.